Vishal, Pankaj. There are two, Vishal, Vishkarma. Very good morning, Shalini, Kamlesh. Chalo then we'll continue our course. We got the basics of all these three modules. One is open loop op amp, one is a negative feedback, and one more we have is positive feedback. Let us understand the designs now. Okay, how to make an amplifier designs. One by one we complete the task. Next keep the surveying. After this, next keep the surveying. Amplifier designs. Amplifier designs. Whenever you say this word amplifier designs, we have to use always negative feedback in these applications because we want linearity for the amplifiers. So linear region is important, non-linear region is not important. But we have studied that linear region will come only by negative feedback, not by positive feedback. Correct? Shamini thus ACL, how it is low. Now I'll explain in this amplifiers. Previously only with the basics of negative feedback I said low, but why it is low in this class we'll understand it. Okay? Just wait, you'll understand it. So negative feedback we are applying. So the first topic we are starting with inverting amplifier. The first amplifier I'm starting with inverting amplifier. We just copied a very simple to understand inverting amplifier. So how to design an inverting amplifier is minus plus non-inverting we just make ground because you want to go for inverting side. You take one resistor here which is R1, you keep the name and you keep this name as RF. We just give the notations like this R1 and RF. This is your input. So if you see this circuit we call it as inverting amplifier, we call this as. How to recognize it's an inverting amplifier is inverting side you have to see the input to tell that it's an inverting amplifier. Anybody want to tell it should be a negative feedback. That is the recollection how to say it's a negative feedback amplifier. Okay, input should be given from inverting, that will tell that inverting action. Amplifier means it should work in linear region, that means a negative feedback you have to see, that will become an inverting amplifier. So now what are the conditions we are applying here? Try to see. So first we are interested to learn voltage gain, how to find voltage gain, closed loop voltage gain, that is AF you write. Previously I have written ACL, otherwise AF you can write. AF means feedback gain we can say. AF is the feedback gain. Or ACL is also same. Closed loop gain ko AF also you can represent. So let us give some notation. AF is called your closed loop gain or negative feedback gain. Voltage gain AF means here AD and AF both terms will confuse you, so try to give the indications. AD in this class we call it as open loop gain we call. AD we call it as open loop gain. AF we call it as negative feedback gain. We call this as negative feedback gain. So both are different. AD is open loop, AF is negative feedback gain. Now I'm not interested to find AD, I'm interested to find AF. But you have to tell that in this amplifier, what is your gain? Suppose my gain, AD, is open loop gain is inside. Inside the gain is AD. Inside the gain is AD. Now suppose the gain, we can do two cases now. Case 1 we can do. Suppose your AD is a high you said in the amplifier. So there are two cases, AD can be low, AD can be high. AD is high you said. Then what is the principle here is V minus will be equal to V plus minus V naught by AD. This is the V minus in negative feedbacks. Now onwards this formula is very important to understand what is V minus and what is equal to V plus. Okay, this formula I got in previous topic where I have been investigated that V minus is V plus minus V naught by AD. So as we said AD is high here, V minus we can write as V plus. So virtual ground theory we can apply here in this concept. So we can apply virtual short theory here. Virtual ground you can say because virtual ground you can call. Virtual ground theory you can apply. Is applicable. Applicable. Because AD is high, so this part we have neglected. So V minus and V plus became same. Now the point is, if I consider this as V minus and if I consider this as V plus, now this current will take it as I1. This current will take it as IF. We'll take this currents. So what is actually V plus? And this diagram is 0. So non-inverting input is becoming 0 in the class. That's why I said it's a virtual ground. Whenever there is a ground you connected to V minus, it's called virtual ground. So V minus will also become V plus, will become 0. So according to this, V minus became 0 in the class. So we'll apply KCL. We'll apply KCL at the point of V minus. It will become, according to KCL, I1 is equal to IF plus I minus is the KCL we can apply. The current entering to the op amp, I1 will be equal to I minus plus IF. I minus is the inverting input, where we said ideally I minus we can make it as 0. Because we have been felt that input impedance is infinite, so no current will exist there. So I1 is nothing but VIN minus V minus divided by R1 is equal to V minus minus V naught divided by RF. Just apply the I1 is equal to IF concept. So I1 is equal to IF. Up to here you can complete simple mathematics. You'll enjoy a lot these topics because only KCL problems. So VN minus V minus. Here V minus I understood 0. V minus is 0. We investigated by virtual ground theory. So what is the trans function we got is? So this is your EF. So now onwards the standard knowledge for inverting amplifiers. These are the best formulas for the op amps. Throughout your life, this formula never changes. So why can't you have a practice now onwards standard formulas? So closed loop gain. Some student asked me, Shabnidas I think, sir, why the negative feedback gain will reduce? Maybe this formulas will explain. Why the negative feedback gain will reduce means the negative feedback gain is depending not on your AD, it's depending on resistors. So resistors wise, you can adjust in such a manner, you can get low gain also, you can get high gain also, whatever you like you can do. But if you want low gain, we'll take the ratio in such a manner, we'll get a low gain for it. Suppose you want 5 gain, you can take 5k below 1k, it will go 5. Like that we can adjust the resistors and you can make the gain. How much you want, you can make the gain. So this is the story. Gain is depending on two resistors, RF and R1. One is a feedback resistor, one is a series resistor. So AF is equal to minus RF by R1. But suppose in the exam, he changed his problem saying that AD is not high, he said. If AD is not high, case 2 will come. Suppose the question we are dealing with, AD is low. But the question is not AD is high, AD is low we are dealing. If AD is low, then automatically your V minus and V plus will not be same. Because here this quantity will exist. V naught by AD is existing, that's why V minus V plus will not be same. Then automatically what is V minus here is, we have to take the complete expression, V plus minus V naught by AD, we have to consider this expression. Okay, V minus V plus are not same, but V plus here in the board we have seen is 0. 0 minus V naught by AD. So V minus will become minus V naught by AD. This is called the situation what you will get whenever you say AD is low. Previously V minus becomes 0 actually when AD is high, but when AD is not high, low, then V minus becomes minus V naught by AD. The same derivation you have to do again with changing V minus value. KCL at V minus if you apply, it is I1 is equal to IF plus I minus I1 will be equal to same IF. Apply the same KCL and find out this answer with respect to AD form. Your VIN minus V minus divided by R1 is equal to V minus minus V naught divided by RF. So VIN minus bracket terms minus V naught by AD you have to keep is equal to minus V naught by AD minus V naught divided by R1 divided by RF. So your analysis will become like this. By saying this you have to understand, if you do practically every time, I think this will take more steps to calculate. But if you do ideally, this formula is very easy to bring it. That's why most of the times we go for ideal analysis, assuming that AD is high. Okay? If AD is low, we have to do some extra work like this. So what is the answer? If I simplify this, I'm writing straightforward answer. V naught by VIN is equal to AF is equal to, it is minus RF by R1. You'll get the same gain. Denominator will get some error here. 1 plus 1 by AD into 1 plus RF by R1. So these two formulas you should have a practice. One is a theoretical formula, one is a practical formula in the class. So examiner can ask you the second formula for 2 marks questions. So you should have both the formulas in your practice. So how to remember this formula? This formula how to remember, a small trick I'll tell you. It is 1 plus 1 by AD you have to write. AD cannot be in numerator, it should be in denominator. Why? Because if AD becomes infinite, 1 by infinite will become 0, the total error will be gone. So always any high quantities we have to write reverse answer. And what is this extra term? You guys remember 1 plus R by R1. This 1 plus R by R1 is the next amplifier the gain. That is non-inverting transfer function it is. So that is the way how we remember. So 1 plus 1 by AD up to that it is normal. So what you have to write extra bracket term is non-inverting gain you have to write. That formula is the non-inverting gain formula. Okay? That is the way error you can remember very easily. So examiner 1 mark question will be like this, 2 mark question will be like this. AD value very low for these problems. You have to solve the complete question. So this is about my first analysis called gain how to calculate. And there is one more question they can ask you is input impedance also they'll ask you. Let us understand the second parameter input impedance how to solve. Only 2 things I can solve here, input impedance and the gains for these topics. So second one, case 3 you can see. Case 3. 3 cases I can do. 2 cases solved. Next is asking, suppose input impedance how much? Input impedance, which is a ZIN. If I want input impedance here, it is a VIN by, it is VIN by I1. This is the input impedance from the diagram. VIN divided by I1. Okay? VIN divided by I1. So VIN divided by I1 is looking at simply R1. So this is the answer we are expecting. According to the circuit, VN by I1 is nothing but R1 is the answer. Shovik, if AD is very low, okay, how can you say that V minus is infinite? V minus is infinite here. If AD is low, this quantity we have taken into account, or quantity liya, then V minus is equal to V plus. According to our problem, V plus is 0, ground we have taken. Then I think V minus will become this answer. Okay, AD means low means you should not take 0 here. Okay, very close to 0 values. What happens? Like that you have done this. Because examiner never gives 0 AD value. AD they'll give some 5, 10 like that. Then this quantity you have to take into account. Don't say that what V minus is infinite. Because we never take AD 0 in the classes. AD infinite I can take for ideal analysis. AD 0 we should not take. AD will have some value. It may be low or high. Never say the word 0. So input impedance is R1. So R1 is in the range of, generally how much range we take R1 is 1K to 10K we can take. So this person said that R1 resistors what you take in the op-amps cannot be more than 10K, 1K to 10K. So if it is 1K to 10K, I can say that it is a low input impedance. It is a low input impedance. So impedance is coming very low in the case of inverting amplifiers. And you can see here, this gain is a low gain. It's a low voltage gain we are getting. Because the resistor ratios cannot be high gain. You'll get low gains. So R1 is a low input impedance, we define, and the gain is also low. So a negative feedback we will apply, the closed loop gain will be low or less. Okay? Low means in my sense, you can say 0. So 1 to 10 is a low gain. If you go for 100, 1000 like that, the gain will increase. Low gains you can take up to 10. Yes, Shovik, this is the first slide I'm teaching. With this, I covered my first lecture today. My first lecture is completed. That is called inverting amplifier complete analysis. Total 3 points you have to highlight in the notes. These 3 results are important in the class. These results are important. So let us start with the second slide. That is called non-inverting amplifier. They're very easy to understand, these amplifiers. First amplifier is ready, inverting amplifiers. You can write down step by step all the things in your notes like this. Gain is coming very less and the input impedance is low. Anupam Das, then I'll ask you how you decided RE resistor in our BJTs. RP resistors, how you decide. The same story here also here. R1 resistor in op-amps or replica of image of RE resistors in BJT. RF, whatever the feedback resistance you are taken, the resistor is an image, a concept of your RP resistors in BJT. This is a, what I can say, link concept we can say. In the coming classes called topologies. So their RE, whatever you say, it is R1 here. Their RB, biasing resistor RB, which is a high resistance, here RF. Here RF resistor is high, like your BJT classes. This resistor RF, here if you want you can write the range. We take generally from 100K to 1 mega ohm we can take. So RF is a high resistance, R1 is a low resistance. They look like our BJT class RP and RE resistors. Okay, that is the impact of this concept. Because the technique here is R1 we call it as, here R1 we call it as series resistor we call. Series resistor. In BJT class, series resistor is RE resistor. That is the reason we are comparing with these resistors. And RF को हम बोलते हैं shunt. It is a shunt resistor we call. Shunt resistor. In our BJT class, shunt resistor is RP. So that is the comparisons which we do. So there are two different names for this. One is series resistor and one is shunt resistor. Why this is called shunt means current will divide. Whenever you go for RF. R1 means series wise the current will flow. So why can't you have these names also better? Throughout your op amps, these names are one is series, one is shunt. Series resistors are low, shunt resistors will be high. So that is the meaning of this amplifiers. Akshant Kumar here, your RF by R1 I can make it high, I can make it low, whatever I like I can do. But there is a rule in the class, you have to make it low only. That means you have to select the resistors in such a manner, you have to design it as low value. Okay? If you don't design low, what happens? The amplifier will go to non-linear region. So we are not interested to go to non-linear. So we have to control ourselves. Okay? They are given some ranges. We'll adjust the range in such a manner, the value has to come close to linearity, not to the non-linearity. That is in my hands only. Here resistors मैं select करूँगा. Okay? In such a manner, it will maintain the linearity. That is the meaning. The resistors high भी ला सकता हूँ, low भी ला. That is my control. You have to bring it to low. That is important. To maintain the linearity, the gain should be less. So can I expect it's clear? First topic. Let us go for the second design in the class. First design is completed. Let us go to the second design. So let me know if you are completed. Please tell me. I'll start doing the second analysis part. And just highlight the things, whatever I have written in the board, just highlight the things, which are very helpful for doing the problems in the coming session. So now onwards, the closed loop gain of inverting amplifier is very simple formula. It is minus R by R1. That means shunt resistor by series resistor. It's not series by shunt, shunt by series. Yeah, Arpita, what you said is exactly correct. Series resistor will be low, shunt resistor will be high. That is the concept. So let us go for second design. Yeah, Akka, both resistors will adjust in such a manner, will bring the gain to low value. Okay. Finally, we have to bring to low value. So let us go for second issue. Concept number 2. Non-inverting amplifier is the next concept. Non-inverting amplifier is a special amplifier. First one is inverting design basic amplifier. Now it's a non-inverting. Non-inverting wise, what is the difference? You can see minus plus. This is your output. The person is here taking input at plus side because you said non-inverting. The only thing is plus side I have taken the input. And the R1 is same here. R1 will be there and your RF will be there. Everything is same. I have not disturbed anything. Only thing is at your inverting side I made just a ground. The positions have changed in the class. Okay. If anybody is asking non-inverting, input should come to non-inverting. The other side where you kept the input in inverting side that should be ground. So opposite analysis we are doing. This is called a concept called non-inverting amplifiers. Let us understand the gains how to develop here. The gains how to develop. This answer will become V plus. This answer will become V minus. We have two inputs again. V plus and V minus. So start with the first concept. Voltage gain. First calculation I'm doing. Voltage gain. AF. You have to find the closed loop gain AF. If you want to find AF in the class, then how to do it? See the logic. You have given input here. When input is given, you will get some output here. You will get some output generated by input voltage. Whatever the current is there, if there is no load here, the same current will go back. So we can take this current as IF. Same current is coming back. This current will go to I1 to the series resistor. So this is the way how the current is moving. This current you can take it as some I0. So this is the way you are seeing current. So in non-inverting system, we will not get current in forward direction. It will come in backward direction because you are exciting here, you are getting output here, that output current is going to ground. Okay, this is an opposite situation. So now the point is, case 1 I am doing first. Case 1. What is that? AD is high I am taking. If AD is high, happily you can write V minus and V plus, both are same. Virtual ground we can apply. But this is not virtual ground here because there is some voltage. So we call this as now virtual short we call. Virtual short. So whenever you have a potential here V plus, we call that name as virtual short. Previously we can say virtual ground in previous topic because that is ground. Now we can say virtual short. That is the difference between a virtual ground and virtual short. Virtual short is a word comes when you take some voltage at the plus point. Then we can say virtual short it is. Both are same. One is virtual short, one is virtual ground. So V minus and V plus both are same. So that means your V plus in the board it is VIN. So V minus is V plus, that will become VIN. So now the V minus value is VIN we have to take. Okay? V minus is VIN. Now if you apply the KCL at V minus point, now you have to write KCL not like this, you have to write like this. IF is equal to, your IF will be is equal to I1 plus I minus it is coming. The KCL has been changed. Previously your KCL is I1 is equal to IF plus I minus. Now it is, this current is going and it is divided into two parts. But I minus has no importance because in ideal op amps we take it as 0. I minus will be 0 in ideal op amps. Current cannot enter into the op amps. Okay? Like this you can beautifully complete the concept. If I plus IF is equal to I1, whatever IF you are seeing, write the KVL for that. V0 minus V minus divided by RF will be equal to V minus minus 0 divided by R1. Apply the KCL for it. What is V minus here is VIN. VIN divided by RF is equal to VIN minus 0 by R1. So like this you are expecting. V0 minus VIN by RF is equal to VIN minus V0 by R1. Okay? So what is the transfer function we are getting here is AF is equal to V0 by VIN is equal to 1 plus RF by R1. So you can see the standard gain check first. The first gain of your non-inverting system techniques. So this is a beautiful gain. So 1 plus R by R1. So like this, he proved that the non-inverting gain is 1 plus R by R1 we are getting. So inverting gain is different, non-inverting gain is different. Inverting gain have negative sign, non-inverting gain have positive sign, and it is 1 plus R by R1. So that is the way how to get the concept. Who is this asking me? Sabni Das, yes. Your I0 and IF will be same until unless if they don't have any load. In the board I have not shown any load. If load is there, then it will be different. If load is not there, we will have I0 equal to IF. Suppose here, load I kept here. If you keep load, then you will have here IL. So you can see now, this current is a combination of these two currents. Okay, you can take load also if you want. If load, if I don't keep, IF is equal to I0. If load is there, you have to show different. Is it okay? Who is this asking me? Vishal, I minus y is 0, please don't ask. Starting say basics, बताया आपको. Don't miss the basics. I minus and I plus are going to the op amp. Input impedance of the op amp is infinite, so no current will enter into the op amp. That's why I minus is a current called inverting current, which goes to the op amp inside will be 0. So that question how you asked here, already number of times we done it. So EF is equal to 1 plus R by R1. Same answer if I want case 2 analysis. Case 2. Case 2 analysis. If AD is low. So we got a hobby here that AD is low means V minus and V plus will not be same. Then what is V minus here is V plus minus V naught by AD. So what is V minus here is? It is VIN minus V naught by AD. So I think in this concept, V minus will become this much. It is VIN minus V naught by AD. So don't waste the time for this type of problems because whatever the gain you got, same gain will come for the next issue. Only thing is error will be in the denominator. But we have taken op amp is same for both the cases. So error is same for both the cases. So you can write similarly directly. EF, you can write directly the answer. It is 1 plus R by R1 divided by, without calculating all these stories, it will take a lot of time for you. Just write the logic. Error in the denominator will be same for both op amps because it's op amp error. Now you can see, how can you remember this error? You can see the error recognition. Whatever you have here, the same image here. So that is the meaning of error recognition, how to do it. So whenever you want to solve the problem, you must have the simple logic. So error is not coming by inverting gain, error is coming by non-inverting gain. And 1 by AD is a common thing for us in our mind. So this is my formula without doing derivation. Unnecessarily don't do derivations. This is a practice you can do straightforward. So EF becomes 1 plus R by R1 divided by 1 plus AD into 1 plus R by R1. Last case is input impedance, we'll find out. Last case is input impedance. Last case, case 3. Case 3. Input impedance called ZIN. If I want to solve ZIN, to see correctly the board, this is minus, this is plus. Plus side you are applying here, your input. This is your output. We have some shunt feedback resistance, that is RF. And we have series resistance here, R1. This is ground. So now your input, we are seeing from here, ZIN. So it's asking you, what is the input impedance of a non-inverting amplifier? Sabni Das, immediately आपको questions कैसे आते हैं ऐसे? Here how error comes कैसे आप बात करते हैं आप? ये formula, whatever you derived, okay? Again you have to do this process, unnecessarily wasting of our time, energy, all these things. I said that V minus, you kept here VN in the previous class. Now just this formula is a पूरे calculations करना. So why to waste the time in our subject? Okay? It is coming this error, whatever you simplify that answer again by KCL method, whatever the answer you got will be same as the previous answer. Then why to do number of times is telling? Okay, unnecessarily blindly, don't keep the concepts in your subject. Logically you study, smartly you do the subject. So whatever the error you got, this error is due to op amp. Op amp error is same every time. It may be inverting you take, it may be non-inverting. Op amp is op amp only. So the error is same I'm telling you in the class. Unnecessarily without doing this calculation here, calculation steps increase क्यों कर रहे हैं? Directly image practice को it I said. Okay? वो point समझ में आने के लिए try करो. Here how error comes ये क्या है? तो clearly दिखाया point को. Just you have to substitute this answer. You have to substitute this answer. Here I said. ये answer से the substitute करके पूरा mathematics करके वो answer आ जाए. Okay? So we are very intelligent in thinking. That's why we don't do extra works like that. Okay? Practice session should be like this. Unnecessarily I never increase the steps. So this is my error, same for inverting and non-inverting. So how to remember also I said it. This is a non-inverting gain error. And 1 by AD you have to keep in mind that it should be reverse because AD should be high value, so it should be reverse is required. Like that instantly a formula आ जाते problem में whenever the question comes in gate exam खत्म. So that formula recollection you are not doing. That is the main problem. You are not understanding the formula and keeping in your mind. If such formula is not there in your mind, you have to do these all stupid steps. Exams में वो steps कौन पूछे आपसे? It's not an interview also. They are asking only straightforward question. Tell me the gain when AD is low. Straightforward you have to throw that answer and you have to finish the technique. Then you will get when you have this type of practice session. Okay, the answer is there. Observation should be done. Okay, this answer should be parallel and this answer is same as previous answer. It's a practice कर. Then you will never forget this type of ideas. Okay, smoothly one by one investigate them. And coming to here, he's asking input impedance from the plus side. Then if I take this answer as, if this answer is I plus is going inside. Now what is your input impedance in the board here? You can see it is VIN divided by I plus will be the input impedance. Same from the non-inverting side. But according to the ideal subject, VIN I plus is 0. So I think your answer is infinite. So I can see the difference between non-inverting and inverting. Inverting systems are telling my answer is R1. Non-inverting systems are telling my answer is infinite. That's an ideal answer. It is practically mega ohms because inside my input impedance is mega ohms. So we are getting high input impedance for this amplifier. High input impedance. So this is the story about input impedance. The previous amplifier is not giving high input impedance, but this amplifier is giving high input impedance. What is the advantage of high input impedance is it can solve the loading effect problems I said. So whenever you have loading effect, I'll suggest you don't take inverting amplifiers. Let us go for non-inverting amplifiers because it will have very high input impedance in electronics. Okay, this will solve the loading effect problems very easily because high input impedance is coming. Like this smoothly you cover step by step in the class. So 2 topics without any pain I completed. So I'm expecting without pain you understood it. Concepts. These 2 topics we don't have any pain I'm expecting. So the results are very important. A results थोड़ा practice करना है as a student. They are not very big formulas to keep in mind. formula is minus R by R1, like that you have to keep in practice. And non-inverting gain will be 1 plus R by R1. These are the gains. And if anybody says some error is there in the bottom, it is 1 by 1 plus 1 by 80 times non-inverting error. Non-inverting gain, 1 plus R by R1. Like that you have to recollect the gain formulas. So I completed my two concepts. Let us go for two more derivations. That is, one is a phase shifter and one more is voltage follower is my next analysis. Complete this two. Complete the second derivation. Yeah, Harsh Mishra, good. Understood, and your orbit is a good thing. Great. I'm thinking that in your notes also, you're highlighting like this. Yes, structures ko highlight karo. Tomorrow class, when I start my teaching methodology and problems, I will have a short notes on each and every formula. We'll try to recollect tomorrow class. Okay? Take short notes, we'll start the class. Complete package of short notes will come for tomorrow on the linear system analysis. By seeing that formulas, we can finish each and every question in your workbook. Tomorrow morning, we have to do some workbook based on this lecture. Nearly a lot of questions we can complete with these ideas. You'll get a good practice. So I think you have done it. Let us move to the next concept. Let us move to two amplifiers at a time I'll teach. That is topic number 3. Here is voltage follower. Next concept is voltage follower. Voltage follower. So what are the conditions for voltage follower? If anybody asks, conditions for voltage follower. In the exam they'll ask you, what are the properties or conditions for a voltage buffer or voltage follower? Voltage follower can also be called as buffer, we can call voltage buffer, which we have seen in common collectors. So the very important point is, input impedance for the system should be infinite, we have to show. Output impedance should be 0, we have to show. And ultimately your gain should be 1, you have to prove it. These three things should be there in your amplifier, then it will become a voltage follower in electronics. It is not the meaning that voltage gain should be 1. Voltage gain also should be 1. Input impedance infinite chahiye, output impedance 0 chahiye. Very good, Arpita. Wonderful. How I am teaching in the same manner if you can write, okay? You will get a very good recollection in the future classes when you study it. Notes should be always neat and clean. That is more important when you study in competitive exams. Okay, with the different colors. You just highlight the formulas every time. That will help you to recollect the subject easily. Some people I think notes will write in a irregular manner. That is the reason when they study, that interest will be gone. But some people will write very beautifully, step by step, each and everything very nicely. In offline classes, I'll see that people who write very neat. That students will study the subject very good. The reason is order of practice. Neatness is more important. Notes should be very neat. All these things you have to take care. Okay? Anything you do, okay, with neat behavior you do it. Then automatically it will come. So whatever I present my subject, the subject will be in a neat manner I present. That's the most important. That's why you'll enjoy it. If I don't teach like this, irregularly if I teach, suppose this is the right topic, next I want to non-linear application, again I can do linear, I think your mind will be gone. So always procedure, a quarter chahiye. Anything you do. Okay? Roy, I think loading effect, एक बार roughly बताता हूँ, देख सकते भूल गया I think you forget. So here, suppose you have a signal source here. This is your signal source. Here you have some RS. We call this as microphone I said in previous class. एक amplifier का example लेकर बताया, एक microphone in electrical sense we can write like this. Now this is your amplifier system. This is your amplifier. Okay, amplifier, we have some input impedance. Now tell me, you have just connected these two. Means this amplifier became a load for your microphone. Okay, now the person is asking, can you send this total PS here? Without disturbance, can you send this total voltage here? Then when it is possible to send that voltage? I want to send this total voltage to that place. Correct. That is possible only when input impedance is infinite. Correct. When input impedance, if you make it infinite, I think, okay, this side current will be 0. You can get the same current, you can see. The current cannot go to high input impedance of your device, which is op amps. So that is called loading effect solution. You have been just joined a load, but I am not feeling that there is a load connected. That is called loading effect solution. If you connect some load to me, if you make a short circuit, what happens? You are getting a loading effect on me. If you make it open, that means there is no load. That is the meaning actually. Okay? That's why high impedance is better always. So let us start the journey on this. Input impedance should be infinite, output impedance should be 0, AB should be 1. This property is how to bring using op amps. So I started my design like this. First I have taken your op amp, non-inverting system. This is your input. This is your input. Non-inverting system I have taken. This is V0. And suppose if I take only RF in the design. Suppose I remove here R1. Just I remove R1 in the circuit, only RF I kept. Okay, but let's just disconnect here. When you do like that, what will happen is, this input wise, you will get some output, natural, same story. You will get some output. You will get some output current, I0. This current will go back as IF. Now can you see that this side we don't have any path, but I think this current compulsory has to go as simply I minus. And if you take here some load, here if you take some load, this load current will be IL. So you'll see like this concept. So I0 becomes IL plus IF, but IF becomes I minus. So what is the proof I have done is, your current IF is becoming here I minus, is becoming here 0. Because we know ideally I minus or I plus will be 0. So that means your feedback current will become 0. That is the main reason series resistor we have to keep. If series resistor if you elevate, this is the story. Your IF and I minus will be equal such that no current will flow in the closed loop. If there is no current flowing, then what happens here? This model will change like this. This model will change like this. This is your output. Can you see that your model will behave like this? Here you will see a short circuit. So this is the change in your model. So whatever the model you prepared, that model is converted like that because current into resistance. Resistance is there but current is 0. If current is 0, I think the voltage drop will be 0. So we have represented like a short circuit. Yes, Alpash. Capacitors, why we don't use it? The reason is only one thing. That is inside amp, not outside. Outside we can use capacitors, all these things. In the next class I use capacitors also. But outside the op amp I use, not inside op amps. Okay? When you're constructing op amp, I'm not using capacitor because of size matter. So this drop becomes 0. If this drop is becoming 0, can I take here the point? This is VIN. This point is your V0 is coming. So this is VIN, that is V0 because this point and this point are same. This is why I'm seeing the class. Now, if I feel that case 1, first I'll do for case 1, I'll do for AD low, I'll do it for. Not AD high. First case I'll do for AD low. Because in the exams most of the time they ask for AD low concept in this lecture. So that's why first we'll focus on AD low concept. If AD is low, can I say that V minus and V plus will not be same? Where is V minus here is? This is V plus here and this is V minus. One is V minus, one is V plus. Then what is the answer we have to take is, your V minus formula is V plus minus V naught by AD is the formula. So I apply now V minus is V naught and V plus is VIN minus V naught by AD you can write. Now you can take common and find the trans function. V naught common, it is 1 plus 1 by AD is equal to VIN. So you can find the derivation like this. You got the output by input, which is your closed loop gain, is coming to be AD by 1 plus AD. So this formula is very important to do for AD low problems. So many times he asked in exams about this formula. So you can see the buffer formula in op-amps. In the buffers, my formula is AD by 1 plus AD. Okay, if it's AD is low. But suppose in the exam, if I make case 2 study, case 2, saying that AD is high. If AD is high, what happens is your AF formula is AD by 1 plus AD. Your AD becomes much greater than 1. As your AD is very high, like 10 power 4, 10 power 6, 1 is not a matter there. So automatically your AF value will become here 1. So this is called as voltage buffer. This is called as voltage buffer. Like this, I proved that voltage buffer property should be 1. So it will work as a good buffer, ideal buffer, when AD becomes more and more high. If AD becomes lower and lower, I think it will not work like a good buffer. It will work like a bad buffer for you. So good buffer if you want, AD should be very high is required. This is a basic story about concept number 3 called voltage followers. The concept is ready. This is about voltage follower designs concept. These two things are important and these 3 points are important for a buffers. Why should I take particularly non-inverting system? I have taken is because they are asking input impedance should be infinite. Infinite impedance comes only for non-inverting, not to the inverting. That's why we have used non-inverting structure to develop the voltage followers. Okay. In our basic transistor analysis, a common collector and a common drain can work like this. But in op-amps, I think this will behave like a buffers in electronics. So don't forget the structure. This is a buffer. Now onwards. A buffer is nothing but a simple short circuit between output to V minus is a buffer technique. Okay. Happily I covered the 3 amplifiers already. This is a special amplifier I have created. The next amplifier is very simple. Phase shifter will come very easily. Let us finish phase shifter here only because it will not take much time to practice phase shifter. So side by I'll finish the 4th topic also called as phase shifter. Phase shifter. Phase shifter is very easy. Easily you can design it. He's asking only one simple issue here. Your AV should be equal to -1. In the further classes, anybody want -1 phase shifter? We have to design it. So -1 whenever you want. My sincere advice, go for this amplifier called inverting systems. This is R1. This is VIN. This is your output. We have feedback, RF. So I have taken an inverting amplifier in the class. For inverting amplifier, what is the voltage gain we got? EF for inverting amplifier is minus RF by R1. So this is the formula for inverting amplifier, correct? Inverting amplifier is minus RF by R1. So only thing is you want -1 there. Then what we can do is, if RF is equal to R1 is equal to R, I take both the resistors, series and shunt resistor, equal resistors. Then how the design looks is, your design looks like this, minus plus, we have resistor R. In shunt also I have taken same resistor to the output. This is also R, this is your input. So like this I have taken. If both resistors are equal, if I take, I think your EF value becomes -1. So this is called phase shifters in electronics. So I completed my 4 topics. 4 amplifiers are completed. 4 amplifiers are completed. So please complete up here. What will happen if one terminal of the op-amp is not grounded? So I can't understand your question, Vidyadas. What do you mean by that? One terminal of the op-amp is not grounded means what do you want to do? You want to give any input for it or you want to leave it? What is your question? Generally, both sides we can give input. That is also we can do it. That is a differential amplifier next topic. One side you can give input, other side we are not keeping anything, just ground we are applying. Suppose if you say your doubt I understood, if other terminal suppose you are not grounded, you just leave it off, which is called floating point. Say that means any noise enters into that plus mode. I think op-amp will do non-inverting effect also. So without getting that disturbances, if you don't want to use it, just make it ground instead. Okay? We should not leave like that. If you don't give any input, just ground it. Otherwise, there's some outside noise if it enters with that action, then automatically disturbances will become your amplifiers. Yeah, the last topic always AD is high on. In this we don't have any storage. AD is high. It is default. It is AD is high. In exam, suppose nobody said about AD, then default it is high. Especially if you say it's okay. Yeah, Divyadas, I think what I said you understood. Terminal should not be open like that. We should give some input for it. Otherwise, if you don't give any input, we have to ground it. Unnecessary noise will trigger your op-amps. Okay? It will give the unnecessary outputs for it. So this completes the 4 amplifiers in our class. 4 amplifiers is completed. Just hardly 4 more topics are there to cover the amplifier designs. So I'm coming to the next 5th topic is T-network feedback technique will apply now. What is the meaning of the T-network? Why you are doing it? Let us understand. Let us understand why we are doing T-network feedback. Let us understand. Yeah, Samresh. If no input is given, we call it as floating. Maybe this type of technology you see in digital electronics, correct? In digital electronics, you see these words, floating points, floating terminals. They're all words will come from digital designs. No, Akash is damaged, 8 pin can I use? That you cannot use because 1 to 7 only they have given the correct indication for each pin. If 1 pin is damaged, suppose you have to throw it and you have to take another op amp because they're very cheap. Okay, op amps will not cost much. ICs nowadays the cost is becoming very less. So number of ICs you can bring it. If one is not working, you throw it and you use another one. Repair we cannot do it. Okay, ICs one time if they're damaged, we cannot do repairs. You have to rearrange it by another ICs. Okay. Yeah. How phase shifting is witnessed in phase shifter. H1 here, nothing will happen here. If I give input, suppose like this is the input. Same thing it will come with phase shift. It will give just opposite to the signal, 180 degrees phase shift. Whatever the signal you have given, same magnitude it is coming, but with just a phase reversal. That is the meaning called phase shifters. Okay. So let us apply the story of fifth one. Concept number 5. Fifth topic is inverting amplifier. Inverting amplifier with T network feedback. Inverting amplifier with a T network feedback. First I have to tell you some analysis to you to understand what is T network feedback. So if you take the basic amplifier, anything you can take. Suppose inverting amplifier I have taken. Inverting amplifier. So what is the gain here? Inverting amplifier. In magnitude, if I say it is RF by R1, you can say. This is the magnitude answer. Inverting amplifier. Okay? Up to here, we have the basic knowledge. But some student ask me, sir, resistor when RF is very high, R1 is very low, we can do high gain. Yes, naturally, high gain we can bring. But here, what is the meaning by saying? The minimum input, the minimum input for an amplifier, is 1 millivolt. Is generally we do for small signals. So the minimum input generally for an amplifier is 1 millivolt to start with. Okay? Millivolts will be getting amplified to volts. That is our amplifier techniques. So my voice signal, when it converts into electrical signal, it starts with a millivolts input. So the first minimum, I can say 1 millivolt. Let us do an analysis now. So Akash Mitra is asking, CMRR is good for non-inverting or inverting? First of all, CMRR board, we should not talk for inverting, non-inverting. Okay? CMRR is a board came by 2 input amplifier. But here we are using only 1 input. So CMRR is a board we should talk for only differential amplifiers, which is my next topic. Examiner never asked you in this topic, calculate CMRR. Okay? CMRR cannot be done for single inputs. Please keep in mind. So don't talk about CMRR for these 2 amplifiers. They cannot control CMRR designs here. So the minimum input for an amplifier is 1 millivolt. Now if I ask you, what is your output? Is your AF, output is AF into VIN. Now you can think in the class, output is equal to AF into VIN. I decided that 1 millivolt is your input. 1 millivolt is your input. AF into 1 millivolt. Just applied it. But can you know how much output has to come so that the op amp looks linear for it? That also you have to have knowledge. So how much output you can maintain it such that in the graph your system will be linear. Means I can give a proposal for this also. The maximum output, the maximum V0 for an amplifier to work in linear region. The maximum voltage for an amplifier to work in linear region is you take it as 1 volt. So these are the important steps. So maximum I'm telling you, don't cross more than 1 volt. Okay, 1 volt is very close to 0. So I'm expecting up to 1 you will be linear. If you go on like that, you will become non-linear in the graph. So I know that minimum input, how much for an amplifier, I have the knowledge. What is the maximum output you have to bring? 1 volt. With this knowledge, how I design my resistors, I'll show you. This is 1 volt, that is 1 millivolt. Now you can write this answer. 1 volt is equal to AF into 1 millivolt. Then can you tell me how much the AF you have to design for this particular input? Like this we are designing first the gain. Then we'll try to select the resistors. Your AF will become 1 volt divided by 1 millivolt. For 1 millivolt, how much I can do maximum? You can see it will become 10 power 3. Can you see that AF is becoming 10 power 3? 10 power 3 means it's not a low gain, it's a high gain. It's not a low gain, it's a high gain. That means in negative feedback also, our gain can become up to 10 power 3. Highest is 10 power 3. Below that 10 power 3, any value you can design. That depends on my calculations here. Output should be 1. Your input should be 1 millivolt or something. It can be 5 millivolts, it can be 10 millivolts. According to that, you set the gain. So that you will be under linear region until unless if you don't disturb these conditions. Now the point is, AF is coming 10 power 3 for this maximum output with minimum input. Highest value, lowest value. If AF is 10 power 3 in the class, suppose if I select any one resistor in the class, suppose R1 I selected is suppose 10K I selected. The maximum resistor I selected is 10K, series resistor. Now I ask you, design RF. In this case, how much the RF will be? Then your formula is AF is equal to RF by R1. This is the formula, RF by R1. So now the point is, RF by R1 is a 10K you have selected, then AF is 10 power 3, then RF will be AF into R1. This is RF value. So how much we are getting RF here is, it is a 10 power 3 is your gain into RF is 10K. So you can see how much it is. Otherwise, for simplicity calculation, what I'll do is we'll take this as 1K. Let us make an easy calculation. 1K will take 1K to 10K you can take. So minimum value is start with them. It is 1K suppose. Okay, 1K. So exactly it looks as 10 power 3 into 10 power 3 ohms. It will be 10 power 6 ohms. That means it is 1 mega ohm. So I have seen the step now. R1 if I take 1K, your RF is telling I should be 1 mega ohm in the design. The only trouble now I got in the class is the resistor RF is increasing more and more. RF value is increasing more and more in the design. When you are taking AF value greater and greater values up to 10 power 3 if you want the achievement, your RF resistor also becoming very high. That creates a problem when you package this total amplifiers in a single IC. It will create a problem again because high resistance 1 mega ohm. So how to control this mega ohms resistance? Okay, it should not be mega ohms. It should be in kilo ohms we want, but you want a high gain is required. Then how to achieve this point? Okay, that is the concept now. Let us make a high gain but with low resistances. How to design it? high resistance. It is becoming a high resistance for this requirement. Then without making high resistances, how to bring the gain to be high value? For this, to make low resistances, to make low resistance, to make low resistance RF, we use a technique. We use a technique, T network feedback. T network feedback. So to make this controlling of RF very high resistance, I'll try to design a T network technique that will make the resistors very low values and it will give the high gain for you again. So what is the trick with Xeno? So this is the backup analysis for you why these people are doing this technique. Okay. Ultimately, the shunt resistor should not be in mega ohms; it should be in kilo ohms. You have to make it. For that, what is the design we are doing? Let us understand. Gain comes high only, but RF resistor should not be very high. It should become a low resistance amount. So like this, you have to understand the fundamentals for any topic. So complete this. Let us apply the technique. How will improve the gain? I'll show you in the class. So our ultimate goal here is that RF resistance should be not in mega ohms; it should be in kilo ohms we want. So like 5K, 10K, 6K, that is okay, but don't go for very very high resistances. That will create a problem in size concepts in the designs. Designing 1 mega ohm is difficult actually in the concept of ICs. That's why we have to go for alternative treat. So let us go for a design now. Let us go for a design now. Okay. Let us go for a design. So how to design this T network feedback privacy? So the T network feedback is, suppose if you take an inverting amplifier now, minus is plus is grounded. We have a resistance here, R1. This is your input. This is your output. The only thing I'm doing here is, I'm just taking here, in place of RF, I'll take it as R2. Okay, in place of RF, we're taking it as R2. And what I'm doing here is, I'm adjusting one more resistor here, R3. And I'm creating here one more resistor here, R4. And I'm connecting to output. As mega ohms is difficult to arrange in the designs, we go for a partition of resistors like this. Okay, 3 combination of resistors I'll take, and it should be a low resistors I'll take. So this combination, we call it as a T network. That means total RF, I distributed into 3 resistors in the feedback. That structure is looking like a T network. That's why we call it as T network feedback. So these resistors all should be in kilo ohms we have to arrange. Then how to arrange in kilo ohms, you can see. So how to get the gain for this topic, let us analyze. So default, you take it as AD is high. Don't speak here low high. Only for high we do these problems. So AD is high. Therefore, V plus is here. Your V minus is here. This current will be I1. This current will be I2. And this voltage will be Vx. Up to here, we'll solve the problem. What is Vx? First I do find out. So if I apply a KCL at V minus I applied, your I1 and I2 will be same. KCL I applied. Your VIN minus V minus by R1 should be equal to V minus minus Vx by R2. But V minus and V plus are same here. That is 0. Virtual ground we apply. So VIN minus 0 by R1 should be equal to 0 minus Vx by R2. So what is your Vx by Vx is equal to? It is coming to be minus R2 by R1 into VIN. So if you see clearly, your Vx is coming a negative answer. And it's a inverting gain we are getting as minus R by R1. So this is coming as your Vx value. If this is Vx, can I say that this is ground point and above is a negative answer? So the current will go upward in T network. Because this answer is a negative answer we got. So higher potential is 0, not the negative value. So current will go from ground to negative value. Negative potential. That's why the current will go upward. These two currents will join and it will come as I3. So this is the path. First investigated what is Vx. Then I found that current has to go upward. So if I apply KCL at Vx, again one more KCL, it is I2 plus I4 will be equal to I3. Apply one more KCL for this to solve this gain expression. I2 is nothing but V minus minus Vx by R2 plus 0 minus Vx by R4 is equal to I3 is nothing but Vx minus V0 divided by R3. So in this formula if you see V minus is 0 here. So we can take this quantity as 0 in the class. So you can see there are 3 Vx you can take common. 3 Vx you can go common for it, and V0 you can bring this side. So we can write V0 by R3 if it comes this side positive. If Vx goes that side, Vx common, it is 1 by R3 plus 1 by R2 plus 1 by R4. We'll get like this. So now this R3, throw it that side, then what is that expression we are getting is V0 is equal to Vx into 1 plus R3 by R2 plus R3 by R4. So this is the way you are getting the expression between V0 to Vx in the problem. V0 to Vx. But here Vx in terms of VIN, we can find out the answer. So we can write this answer as V0 is equal to minus R2 by R1 into VIN, substitute Vx equal to VN relation into this total term, 1 plus R3 by R2 plus R3 by R4. So what is the gain here? AF gain is V0 by VIN is equal to minus R2 by R1 into 1 plus R3 by R2 plus R3 by R4. So without taking mega ohms resistance, with kilo ohms we can solve the purpose. Mega ohms resistance is difficult to take in designs. So with kilo ohms you can see how I improved the gain for it. So it is only previous answer is minus R by R1, but now present answer is minus R2 by R1 is also there into 1 plus R3 by R2 plus R3 by R4. This is a incremental gain we got, increasing of gain. So this is called high gain technique. High gain. This is called high gain. So we can increase the gain whenever you have a very small inputs like 1 millivolt you have. At the time the situation is we need 10 power 3 gain. Also the system will be linear for you. At that time the gain has to increase. In negative feedbacks, the RF resistors we cannot make it to close to 1 mega ohm like that. So to kill that one, what I have done is T network technique I have used. Okay? T network techniques we have used without going up to mega ohms of resistance. So high gain will be achieved by this technique. So that's why in exam point of view, whenever they ask you T network feedback questions, the meaning is gain questions they'll ask you. What is the voltage gain? Means the formula is this one. Minus R2 by R1 is a normal gain, which is called inverting gain. Extra is 1 plus R3 by R2 plus R3 by R4. The only thing is R3 will fall on 3 resistors. R3 by R3 becomes 1, R3 by R2 plus R3 by R4. So these questions came number of times in your competitive exams. They are called T network technique problems. So this is the main purpose why you use this technique. High gain, if you want in negative feedback systems, this technique you can use it. By taking number of resistors, you can boost up the gain how much you want. But a single op amps cannot do that with the 2 resistors. But this can do very easily by taking a reasonable resistors. In kilo ohms we can do it. Divyadas is asking, can we go by connecting in series? Divyadas, again, if you connect like that, okay, in series if you connect, it will become very lengthy design here. Okay, then how to design is, if you have 1K like that, you have to take a series of resistors like that. Okay, but here the technique of T network will tell you that how the gain is improved by this logic that you can see. If series wise if the game is over, then scientists have done the series one. Here they have a special idea called T network technique. What is the reason is, in T networks these two currents will add and it will generate the new current called I3 that will increase the gain automatically. Samlesh, here one thing you understand, here in this design, space is one concern. That space is for inside op amps. Outside op amps, any number of resistors you take, no problem. For instrumentation amplifiers, because in instrumentation size is not a matter. But the problem here is mega ohms impact resistance we cannot take in the designs. We have a choice of taking kilo ohms in electronics. Mega ohms resistors we cannot take in my designs. That is the main reason we have 1 to kilo ohms designs here. Okay, mega ohms are not preferred in the designs. If you want to convert into kilo ohms designs, this is a better history. Externally, how much size you take, that is not about us. Size always think about inside, not outside. Okay, outside is not the size matter. Inside the size matter. Here our achievement is mega ohms resistor is not preferred in practical designs. That's why we have entered into kilo ohms design. Because this amplifiers most probably be used for instrumentation techniques. Because the amplifier system, what you have been prepared in electronics, is a big box actually. In your BTech level, I think when your professors are teaching, side by there will be some amplifier box, will be there, rectangular box. That we are not holding it, we are keeping side by. So for instrumentation, size is not a matter. But mega ohms resistors are not good for designing. That's why we will go to kilo ohms design, and it may be size is big also, we can achieve the gains here. That's the meaning what I want to tell you. Okay? So please complete, the story is ready. This formula is very important. This formula is very important. If you want to achieve the high gain, this is the formula. At the same time, is there any change in your input impedance? If I ask you, there is no change. Your input impedance is again R1 only for this concept. Can I add this point? Input impedance, there is no change. Input impedance we got same. Only thing is gain is changed. Okay? Input impedance is R1 only, but only thing is voltage gain I changed in the class. Gain is R1, but the gain is different. Gain is different. Arpita, you're asking previous slide. Okay? Previous slide, देख सकते हैं आप. This is previous slide. You can write here one point. Practically, mega ohms is not preferred. The main problem here is mega ohms resistance generally will not prefer in the designing. Okay, that is the main cause why we are not showing much interest in mega ohms. Only kilo ohms resistors generally we use in electronics. So externally size is not a matter. That is the reason I have taken 3 resistors to analyze this topic. Not only 1T, you can make 2Ts, you can make 3Ts, like that you can design. Examiner can ask you with a 2T also. At the time you have to go for one more KCL and one more action and you have to find out the answer for it. It's only one KCL method. I have applied 2 KCLs I applied. If you have one more T, you have to apply one more node and we have to solve the problem. Okay? Maximum you can apply 2 T networks. It's 1 T applied. So let us close this matter. This is the non-inverting system techniques. The same thing if I want to do with a non-inverting also we can do this. Next topic is non-inverting also we can do this. So how to find out the gain for non-inverting? Voltage gain how much we get for non-inverting? Let us calculate the next step. What is the next step? I think this concept is considered 5th one. Next we are going for 6th one. Non-inverting amplifier. Non-inverting amplifier with the T network. Feedback. So go for non-inverting system technique. If I take now non-inverting system, this minus plus, we have VIN, we have output, we apply T network here also. This is R3, this is R4, the ground, this is R2, this is R1, this is ground. So T network we are applying, but here the currents will go in reverse direction. This is I0. Now this current will be I3, it will go opposite now. This current will go I4, this current will go I2, and this current will go I1. It's an opposite knowledge. And this virtual point will become VIN directly. Virtual point is VIN. This is AD is high. These problems we have to do for AD high concepts. Because amplifier gain we want high means this technique is default AD is high. So first how to find this answer. If I want to find Vx, you can take a KCL at VIN point. That is V minus point otherwise. V minus point, KCL I am applying. I2 is equal to I1 it is happening. I2 is equal to I1. It is Vx minus VIN divided by I2, divided by R2. Divided by R2 should be equal to VIN minus 0 by R1. This is the way you are getting the relation. So if I want to find out the relation between these two, it is Vx is equal to 1 plus R2 by R1, which is non-inverting gain, into VIN. This is a V plus. That is the reason the current is going down, because this is a positive answer. Previously we got a negative answer, now we are getting a positive answer. Okay, please complete this derivation. Only 2 more amplifiers to cover today class. Special parameters tomorrow morning I'll teach. let us complete the amplifiers at least. So Vx answer is 1 plus R2 by R1 into Vi. So up to here, the story is completed. Next we'll apply KCL at Vx. KCL at Vx point. If you apply KCL at Vx, this current is entering, these two currents are leaving. So I3, you can write it as I2 plus I4. So just you can complete the task and see that how much the expression is coming for this. Only two KCLs will finish the problem. So I3 is nothing but here, V0 minus Vx divided by R3 is equal to V0 minus Vx by R3 is equal to Vx by R4 plus Vx minus Vin divided by R2. This is the currents I have written. So here what is happened is V0 by R3, if you keep one side, Vx are going common, we have same manner like previous topic, 1 by R3 plus 1 by R2 plus 1 by R4 we are getting. But here extra what we are getting is minus Vin divided by R2 we are getting extra. Extra R2, Vn by R2 is the ratio we are getting here. So this R3 if you throw that side, it becomes Vx into 1 plus R3 by R2 plus R3 by R4 will come. That R3 if it enters, and here minus R3 by R2 into Vin. That R3 will go for both the expressions. So what is Vx? If I substitute here this formula, it will be 1 plus R2 by R1 into Vin into 1 plus R3 by R2 plus R3 by R4 minus R3 by R2 into Vin. So you may get like this concept. So if you take the common here, Vin if you take common here in the class, I think trans function you can find out. So finally you got the expression for this concept. What is the final expression here is V0 by Vin if you take, which is a closed loop gain AF. The answer you can write it as 1 plus R2 by R1 in brackets into 1 plus R3 by R2, R3 by R4 minus of R3 by R2. So actually this is the gain which we are getting in this case. So finally the gain is completed. This is the gain I am expecting. The formula I created this one. This is the formula. So in your gate exams generally when they ask you these questions, they never give these resistors like this R3, R4, isn't it? R2, R3, R like that. So R's will get cancelled actually. So if you get this formula straightforward, throw that R values, you get a quantity. Very easily you can find out the value because they'll give equal values. Rahman here, Vx positive. I am not assumed here. I just calculated here. You can see this is Vx. Vx हमको positive मिल रहा है. मैं assume नहीं किया. Calculate करके positively cover. Okay? Because of positive, the current is going down, not up. That he mentioned in the concept. And what about the input impedance? Is there any change here? Means your input impedance is not disturbed. It is infinite. So we are getting input impedance like previous topic. Input impedance is not changed. Only thing is gain change. Your voltage gain became high. T networks wherever you are using, voltage gain is becoming high. Voltage gain is high. So in negative feedback, we can increase the voltage gains. Only the trick we have is T network trick we can apply. Okay, the main purpose to increase the voltage gain in negative feedback is T network techniques we can apply. So with this friends, nicely we completed the situations of inverting systems and non-inverting systems. The final goal for this is one more special amplifier is there called, okay, one more is a differential amplifier is there. Till now CMRR we cannot calculate because they are single input systems. But CMRR is a word comes for two inputs. That's why the last topic we can measure the CMRR. Here we cannot measure because it's a single input we have taken. Single inputs we cannot teach CMRRs. That is the reason you have to design a CMRR circuit in such a manner that has to give infinite in your differential amplifiers. That we'll see tomorrow class how CMRRs I'll calculate. Today only we'll see the gain how much and how the input impedance we can calculate. Tomorrow class I'll take the example of a differential amplifier and I'll prove that how the CMRR should be infinite. That is tomorrow calculations. Today is only gain factors I'll find and one more factor is that quantity. What is that? Gain and input impedance. Gain and input impedance we'll find out. Sabnidas, again you also asked the same question here. Vx, are you assuming positive polarity? इधर मैं क्या बता रहा हूँ here? Vx हम assume नहीं किया, find out क्या है? 1 plus R2 by R1 into Vin. That's a positive quantity. Therefore I have written positive. Then I made it as I4 in the downward direction. Okay, Arpita. So let us go for the final issue here. I'm waiting. Just to complete it, we'll come to the last two topics remaining. One is the differential amplifier story. Last one is instrumentation amplifier. Today I can finish up to here. Tomorrow we can start with the special parameters morning class, 8 to 10. It will take 2 hours to explain that 4 parameters. After that, we'll start the journey on problem practice. Tomorrow, I think by afternoon, we are covering the workbook practice, all the issues we are going to cover. So in the afternoon session, we'll start one small module is there called mathematical operations. Mathematical operations hardly takes 2 hours time to deal that formulas calculations. So by 1 o'clock, we'll complete total workbook up to amplifier designs tomorrow. By 2 to 2 o'clock to 4:30 or 5, we'll complete the mathematical operations tomorrow. So by tomorrow, if we can complete up to mathematical operations, day after tomorrow is only one class will be there. That is called non-linear applications. One of the complicated subject and very important topic in analog electronics. So step by step, I have to teach like a story. That's why the total day I'll take is non-linear analysis. One day, complete picture. So that options will be completed smoothly. Workbook also will be completed on the same day. So next day, we'll start designing on, I think Friday we are going to start negative feedback amplifiers in morning class. Afternoon class, we'll start oscillators. If it is not completed, Saturday we'll take oscillators. In afternoon class, I'll teach you power amplifiers. That's a separate module I want to teach for you, power designs. So I'll see that time permits, I'll teach power amplifiers. With that, we can start the complete approach. And only for ESC student of electrical students, I'm promising you that the theory content, which is for PNX theory, the basics, I'll give as a presenting as a video at the end of the all lectures. That you can see it, you'll understand the basics. Because there are very simple things. What is a P-type, what is an N-type, what is an intrinsic, what is an extrinsic. Beautifully explain the points for the other batch. So that video you can see, that will complete the analog course. Okay? Like that we'll compromise the subject. Let's see today goal we can reach now. Last two topics are there. So let us start. Let us start our journey for the next topic. That is seventh one we are entering, called as differential amplifier. Differential amplifier. Keep the heading differential amplifier. So how to design a differential amplifier, you can see. Suppose if I take minus plus, this is your output V0. Here some R3 resistor I have taken, and here I am giving some input as V1, and here input as V2. This is R1, and here we have a resistor RF. Suppose I design an amplifier like this, where you have both inputs at a time. This is one input, this is one input. So what will be the result? Somebody asked me, can you solve this problem? Then what type of concept or intelligence we have to use? That is important. Up till now I know inverting how to do the question, non-inverting how to do the question, everything I know. But first one point is very good here. These all systems we are doing not in non-linear region, we are doing in linear region. That makes me happy to start the concept of superposition theorem. So when the system is in linear, when the system is in linear region, we can use superposition in the class. We can use superposition. This is the good point here. What the superposition says is, at a time it's not required, you can solve one by one. Okay? At a time it is not required. You can solve one by one and make it addition, you can finish off. So output you can write as V01. At the time, your V2, you make it 0. That is your non-inverting output find out. Next to find out V02, at the time, your V1, you make it 0. So this is the way you find two answers. You are assuming that your V1 is 0, at the time V2 we are finding by the help of inverting techniques, and V2 0, V1 we are finding a non-inverting techniques. So this problem is nothing. We can easily solve this problem by this technique. If I want to solve the first answer V01, so what I'll do is, I'll take the op amp, minus plus. Plus side we have R3, we have V1, this is R1, this is ground, this is output, this is RF. Like this you are seeing the problem. This is the first superposition theorem I am applying. Can I say one thing? You may take R3 or not, the current here going is I plus, is 0. So can I say that this becomes V1 in the class? So wherever you have taken the same answer you can take here also, because no current will enter. So resistors in the exams you may take or not take. We don't bother the resistor because current cannot go to op amp. That rule you have to apply. So this answer will be same. Otherwise you can write like this. This answer you take it as V plus you take here, this is V plus. According to the story, now we'll write the answer first. This is a non-inverting amplifier. The formula will be V01, this is V01. It is 1 plus RF by R1 is the gain which we studied into V plus is my answer. It is not V1, it's a V plus, correct? Because non-inverting exactly have given the input and we found this formula. So this will become the input, not this one will become the input. But perhaps these two answers are same. So here V plus and V1 became same. You will enjoy that answer. Now what is the answer here is V01 will become 1 plus RF by R1 into, simply you can write as V1. Can you take this as equation 1? First answer is finished. Second answer is second one. What we'll do is second case, the minus plus here resistor R3, we'll just make this as ground. This is R1, this is output, this is RF, this is your V2. This is the second case. Inverting side I'm finding the answer. Your formula V02 is simply minus RF by R1 into V2. This is your second equation. So first answer, second answer completed by the basic knowledge, inverting systems and non-inverting systems. So what is the overall answer here? So finally my answer is, for this problem, your V0 will be equal to 1 plus RF by R1 into V1 plus minus RF by R1, this bracket you can keep into V2. This is the way how to find out differential amplifier output. This is the way how I am finding the V0 for the differential amplifiers. So this completes the meaning how to find out the differential amplifier input impedance. Sorry, how to find out the output voltage for the differential amplifiers. So till now you complete up to here. You do up to here the concept. And if anybody asks you how to find out the input impedance for the circuits. Okay? Input impedance if you want to find, how to find it, see. Generally for this amplifiers, input impedance if you want to solve, what is happening here is, so if I want to find some input impedance for this, input impedance which is Zi, this is R1, this is RF, this is V0, this is R3. Suppose in between I have given some input. Like this they will give in the exams. If I give some input like this in the class, okay, and if I keep some resistor also here, some resistor I am keeping R4, then I ask you what is the input impedance of this circuit. In the middle is asking find out the input impedance. Now what is the trick we can use is this potential, both are same. You can apply virtual short theory concept. You can make these two answers. This two became a short. Like this you can make a virtual short. There is a virtual short here. So whatever the current is flowing here, this current, II, basically it has to come same here, II. So it has to rotate this current inside the loop. So this is the trick. So if you want to find out the input impedance of this loop, your input impedance will be VIN divided by II will be equal to R1 plus R3 will be the input impedance. Just you have to take a combination of these two series resistors. R1 plus R3 will be the input impedance. But R1, R3 are low resistors only because this is kilo ohms, this is also kilo ohms only. So can I say that this is a low impedance again? So differential amplifier is also giving low impedance. Differential amplifier is also giving low impedance. Okay, it is also giving low impedance. And if you see the gain also, if you take the difference like this, it is giving low gain. Gain is also coming less only. So it is also giving low impedance and low gain. So this completes the story about this concept. So finally, what I want to tell in the class is, any amplifier you have seen in the class, one amplifier if you have high input impedance, okay, other case we are not getting the other issues. So the main importance today class is, for any ideal amplifier, 3 points we must have at a time. One is high input impedance is required, high gain is required, and high CMRR is required. These 3 points, which amplifier can give, that amplifier can become the ideal amplifier. But this problem, this differential amplifiers cannot give this input impedance high, cannot give high gain, but they can give high CMRR. If you can design properly this circuit, tomorrow I'll show you, it will give high CMRR. So only this circuit have the ability of CMRR technique, but remaining things it's losing. Like the inverting systems, if you take, it does not have high input impedance, it does not have high gain, but high gain chahiye to T network I can use, but impedance will come less only. But CMRR cannot exist in the topics. So next topic is non-inverting system. In that we can get high gain, we can get high input impedance, but CMRR will not come. So these 3 properties has to come at a time. So let us write a conclusion to start the final issue in the class. Summary of Dirac portrait. In inverting T network, ZIN is not infinite, I said in the class. I have not said inverting topic mein ZIN. ZIN, who said for? I have not said. I said ZIN is R1, I said. Inverting systems mein, it is R1. In non-inverting, we will get infinite. Inverting ke liye, we will get only R1 will come in the class. So let us write some conclusion. It is better for you. Up to know what you done, why these amplifiers are not ideal amplifiers. I'll show you the conclusion. Okay? So let us write one conclusion to make the final topic in the class. Today, that is the last topic today. Final class is instrumentation amplifier. Input impedance, nothing here. Who is this? Divya Das. ये दोनों को virtual short किया मैं. When you virtual short, this is a closed loop. So this current will go in series in the loop. So R1, R3 will be the input impedance for R1 plus R3. Okay? So let us write a conclusion of this topic. Complete topic or conclusion एक बार लिखते हैं. So you can write here one conclusion of this class. Up to now, what we have studied, the meaning I'll explain. See here. For an ideal amplifier, for an ideal amplifier, we require first one, input impedance should be infinite. Second one, your AF closed loop gain should be infinite. High gain, high input impedance. And point number 3, CMRR should be infinite. These 3 points I want. You take any amplifier in our class, till now what we discussed. I think these 3 properties at a time we are not getting in the class. Let us write one by one. First, if you take inverting amplifier, you can see the trouble of inverting amplifier is inverting amplifier. First point, your input impedance is low is coming. You think low means 0. Ideally you talk. Low means you write 0, high means infinite. So input impedance infinite baat kare, but 0 there. Second point number 2, your AF, he said that I can do infinite by the technique called T network. By using T network technique, I can make AF infinite. That is not a problem. And point number 3, CMRR will not exist, means 0. CMRR will not exist means it cannot make common mode rejections. So 0 will come. So 2 points are unsatisfied. Only 1 point is okay. T network technique use करके gain increase कर सकते हैं. So the next one we have is non-inverting. Amplifier. In this, what is the advantage we got? You can see. In non-inverting amplifier, we achieve 2 advantages. Input impedance infinite we got. This is one ideal achievement. AF we can get infinite by the T network technique. But one problem is here. That is CMRR we cannot get because it's a single input. So common mode rejection we cannot do it. So you can see the beauty as these 2 we got, but here you got failure. In the second topic. First topic, 2 failures are there. Second topic we have 1 failure. But last one more topic is there. That is the differential amplifiers. If you go for a differential amplifier, I think your input impedance we are getting 0, low. Your gain, AF is coming 0, and CMRR, here we can design infinite. Last case only we can do it. First 2 points we cannot do it because low impedance I got, gain is coming low. T network techniques we cannot use in differential amplifiers because it will disturb the differential techniques. So I think only input 0 ho jayega, AF 0, but CMRR infinite. You can see any amplifier is not satisfying these 3 conditions at a time. So who will satisfy all these conditions? Then only it can work like a audio amplifier in electronics, which is called our basic amplifier in our classroom. So that's why it got the name as instrumentation amplifier. You have to design an amplifier in such a manner, it has to give all the 3 properties in the system. High input impedance it has to provide, gain also should be high, CMRR also should be high. But he said one important point, size is not a matter here because you're talking instrumentation. Instrumentation size is not matter. So how many op amps you like you can take, how many amplifiers you like you can take, but all 3 properties at a time you have shown in the class. That is what design called instrumentation techniques. Then our experts started designing it. One person proposed a 3 op amp design. With using 3 op amps, he said that I'll bring ideal amplifier. And another person said I'll take only 2 op amps, I'll bring the ideal system. Like the 2 different proposals we have to study in the class. First proposal we complete, let's see. Second proposal we see next. Last 2 concepts, which are very interesting concepts, let's see. So previous slide somebody is asking. Complete कर दीजिए. Last topic. So we'll finish the circuits and we'll stop the class. Just take up to here. Sir, what bottle थी? इतना टेबल लेना है. मुझे अंदर टी नेटवर्क सीरीज में कैसे लेते हैं यार? थोड़ा थिंक करो. टी नेटवर्क इफ यू टेक इन शंट, टी नेटवर्क कभी भी कैसे लेते हैं? शंट में लेना बिकॉज इनपुट 1 कनेक्ट, आउटपुट 1 कनेक्ट, मिडिल में एक टी चाहिए हमको. वो सीरीज में कैसे डिजाइन करते हो आप? अननेसेसरी लॉजिक से. So it is completed. Great. Now come to this is the present slide. In all these 3 we don't have ideal amplifier, we are not getting. So how to make an ideal amplifier? We'll see. we'll design an instrumentation amplifier using 3 op-amps. The 8th topic we are designing, we can say 8th topic called instrumentational amplifier. Instrumentational amplifier using 3 op-amps. Instrumentational amplifier using 3 op-amps. How I design the ideal system, you can see. First I'll start with the simple logic. Differential amplifier I'm taking as an A3 op-amp. I start with A3 op-amp. This is your output P0. Here minus, here plus. Here I'm going to design a differential amplifier like this. This is R1, this is also R1. We'll take this as R2 and this as R2. Like this we'll design it. Okay, this is a style of differential amplifier. We can take some R2 extra arrangement. We'll give 2 inputs here. So up to here, we have the differential diagram. Differential means in some cases we can remove it, R2, some cases we can keep it. If R2 if you keep there, we'll get CMRR infinite. Tomorrow class we'll try to deal this concept. How to calculate CMRR, tomorrow I'll explain you. But this circuit can give CMRR infinite directly because there is some arrangements I have done. R1, R2, R1, R2 symmetrically we made. Whenever you make symmetrical system top and bottom, automatically any common inputs goes, it will reject it. The trick tomorrow we'll calculate. At this point you feel that the circuit have one important step, CMRR equal to infinite. We can design with this circuit. But high input impedance we cannot get, high gain we cannot get. There's only one thing it can do is CMRR infinite we can get. How it is coming tomorrow morning, wait up to tomorrow morning. Tomorrow morning is my job is how it is coming infinite, this circuit. I'll explain. CMRR is infinite. With this arrangement I can do it, but you have problem of high input impedance. That's why what I have done is, we have taken here one op-amp extra like this. This is a plus minus I have taken in this manner. The input whatever I want to give here, I'll give here now. This is A1 op-amp, this is A2 you take, A2 op-amp. And we'll take one more op-amp here. This is minus, this plus. You take this as V2, this is another op-amp below, that is A1 op-amp. Like this 2 op-amps I have taken. And I just connected a feedback with some resistance here, R. I close the loop with R. And again here I have taken resistor with R. In between these two, I am joining these two components by one more resistor called as Rx. Like this some arrangement I have made in these 2 op-amps. And finally I am connecting this point to this point, and I am connecting this point to this point. Like this I arrange with the system. So please draw it. This is called 3 op-amp design. 3 op-amp design I made. A1, A2, A3. 3 op-amps. So this is called an instrumentational amplifier we said, where you must get all ideal properties in the class. All ideal properties you must get. One thing is very clear, from the differential amplifier CMRR equal to infinite, we can expect here we have taken 2 inputs, but non-inverting we have taken. So here input impedance, we can take it as infinite. Anything you take for non-inverting, it is 0, no current will enter. Here 0, no current will enter. So 2 important points I completed in the derivation. Because of taking non-inverting op-amps at the initial stage, your input impedance is infinite. At the final stage I have taken differential amplifier, that's why CMRR is infinite. So 2 things I covered like this. Only one property we have to prove in the class, that is gain. If the gain comes high, we got all the properties in the class. One is due to differential amplifier, one is due to non-inverting amplifiers. This is the way how he is getting the total properties at a time. So if you group the op-amps, we can get ideal system. So 2 non-invertings I have taken at the input, last stage I have taken a differential amplifier. So how gain will increase for this topic? Let us see. We'll assume that here V2 is greater than V1 we'll take. We'll assume that V2 voltage is greater than V1 voltage. When this is greater, I think the current will start to flow this side. From here the current will start to flow. High current is coming from here. This current cannot go to op-amp because it has to go directly to the inverting side, so it will not go. The same current, whatever you have I, this current will go to Rx. Same current will go, but it cannot go to the op-amp again because the input impedance is high. Again the same current will go I here. So if you see perfectly this concept, according to the virtual ground, this point is V2, this point is V1. This is a virtual point. This is V2 here, and this is V1. Virtual point applied. So this is V1, V2. Okay? Then we'll take this answer as some V2 dash and this as V1 dash. Because we have some drops here. We'll take outside this network to understand more better. The network is like this. We have R. We have R here. Next we have Rx. Next we have R. Here bottom side is V2 dash. This is V2. This is V1. This is V1 dash. And the current is going same. I. Same current is going I. Same current is going I. So this is the situation. Because of current drawn in the circuit, these 2 drops are not same. Your virtual short point and your V2 dash will be different because R is there in the middle of the circuits. Let us find out these 2 answers. What is V2 dash and what is V1 dash? If you see in the board, your V2 dash, simply I can write it as I into R plus V2 is my answer. एक बार understand करो कैसे लिखा? First answer I have written is this voltage is equal to current into resistor plus V2. V2 is nothing but this total voltage. So V2 plus IR will be V2 dash. And what is V1 dash? V1 dash means current is going towards that side. So V1 dash will be minus IR because current is going towards that side plus V1 will be the answer. So these are my 2 currents in the class. Sorry, 2 voltages in the class, V2 dash and V1 dash. Now using with this trick, can we find out the differential amplifier output will be how much? If I want to solve this, let us take the op-amp separately like this, differential amplifier. This is minus, this is plus. We have a resistor R1, this resistor is R2. We have now this as V2 dash and this is R1, this is R2, this is V1 dash. These are the inputs are going to the differential amplifier. So these 2 answers are already verified how much they are. These 2 answers, these are my answers coming from your network. So that are going to the A3 op-amp. That are going to A3 op-amp. So you know how to find out the superposition theorem formula apply करके. Straight forward you can find out the answer. If I write the answer V0 directly, this is V plus here. So 1 plus R2 by R1 into V plus you can write plus minus R2 by R1 into V1 dash you can write. Just superposition theorem, straightforward answer. But here, because of R2 here, this is the current flowing here where V2 dash and V plus are not same in this network. In this network, V plus is not equal to V2 dash. So both are not same. Then how to write V plus is voltage division rule you can apply. 1 plus R2 by R1 into what is V plus here is V2 dash into R2 by R1 plus R2. Just you can write the voltage division rule there. Okay? Plus minus you can take R2 by R1 into V1 dash. You can simplify this answer and see how much is coming. So I think this LCM will be, it is R1 plus R2 by R1 into V2 dash into R2 by R1 plus R2 minus R2 by R1 into V1 dash. R1 by R2, R1 by R2 is cancelled. So finally we are getting the output as, कितने आ रहे हैं output? R2 by R1, if you take common, it is coming as V2 dash minus V1 dash. So this is my output in this differential amplifier. So finally I solved what is my output. It is coming as R2 by R1 is the gain, this is the gain into the difference of your input voltage, V2 dash minus V1 dash. So we'll close the subject after this derivation. So the next week we can be ready for networks course. Just finally we'll end up this formula. I think tomorrow when I come back, 8 o'clock, just first I'll complete the one more design called two-stage op-amps. कैसे लिखना वो concept बता दो. After that we'll start the parameter calculations tomorrow. So today we'll end up with this idea. So V0 is R2 by R1 into V1 V2 dash minus V1 dash. If we get up to here, we can solve the answer now because we know what is V2 dash and what is V1 dash. So we can write here output is equal to, after this step, I have been explaining this step now, so don't get confused. So that step I'm writing again here. R2 by R1 into V2 dash here is IR plus V2. This answer you substitute. Minus of minus, it will become plus IR. Minus V1 will come. So V0 will become R2 by R1 into 2 times IR plus V2 minus V1 common. So like this you can simplify the concept. Okay? You can simplify the concept. So what is I here? According to the board, if you see, I can be represented as simply V2 minus V1 divided by Rx. We can write. I can be represented as V2 minus V1 divided by Rx. Okay? So we can substitute this answer here in this formula. So output can be written as R2 by R1 into 2 times of V2 minus V1 divided by Rx into R plus V2 minus V1. So you can see the formula. Your output is R2 by R1 into 1 plus 2R by Rx into V2 minus V1. So the gain AF is V0 by V2 minus V1. It is R2 by R1 into 1 plus 2R by Rx. So finally I got the closed loop gain in the class. This is called closed loop gain. So I feel that previously our gain is very small. Our gain is very small. That is only R2 by R1 in the class. Okay? If you don't have that 1 plus 2R by Rx, if you don't have 2 op-amps, that quantity will not come. Only R2 by R1 will come for this problem actually. But if you are adding 2 more op-amps, we are getting an extra factor of 1 plus 2R by Rx. That will increase the gain in a beautiful manner. So we have the high gain here from this concept. We got high gain, which is we can treat it as infinite. So we got high gain at a time. We got high CMRR, we got high input impedance in the concept. Okay? Rahman, I tell to the sir to take, if the class is supposed completed by 4:40, your class will start by 5:10. Half an hour break will be there, don't worry. Okay? Because sir is here only, I'll tell to him what the time is completed according to the sir will take. Okay, don't worry. Half an hour compulsory, sir will do the break for it. So I'll just compress this. Here I'm going to stop the class. Tomorrow class I'll extend my concept from here. So you can copy it nicely. I'll keep the total slide for you like this. You can just copy it. Maybe I think for writing it will take some 5 to 10 minutes. So you can start the class at 5:15. Okay? Network sir will start the class at 5:15 here. Don't worry. I'll tell to the sir to start at 5:15. So you can start at 5:15 networks. Okay? Now smoothly you can write within 5 minutes and you can stop. Tomorrow I'll start from here. Divya does कैसे बोलते हैं high gain कैसे आया again you are talking R2 by R1 into 1 plus 2R by Rx. We got an extra factor or not? If you multiply these two things, we can achieve the gains. Close to 100 to 1000 we can achieve it. Okay? How high gain you are telling again? Only R2 by R1 is low gain. If you multiply with some extra factor, it will increase to the high gain. Thus, if V1 becomes greater than V2, then you have to start current like this now. You have to teach like this. Then you will get V1 dash minus V2 dash will become your answer. V1 minus V2 will come in the formula. Just only the difference will change. Okay? Which is higher. According to that, the difference will come. So this is the today class analysis. So I'll stop here. So you can take the break. Network students around 5:15 sir will start, not at 5 o'clock. So relax for some time and start the class at 5:15. Okay? So tomorrow morning again my class will be 8 o'clock.